In this video, we're going to talk through another transformation, reflections. So far we've talked about translations, and now we're moving on to reflections. And we said, remember, reflecting something is like flipping it over a certain line. So this first example says reflect triangle JAI in the x-axis. So if we were to do that, you were taking that, and if I use tracing paper, I can see if I flip it in the x-axis, like that, make sure we're back here, this is what that reflection would look like, okay? What I see is that if I am up 2 units from the line of reflection, I can go down 2 units, so it's the same distance from the line of reflection, just in the opposite direction. And when we have a horizontal line, that means going, if I was going up, now I'm going down. So for example, if I were to graph this, instead of going up 2 from the x-axis, and I guess there's something else I should say, when you're doing a reflection, it's always good to graph a line of reflection. So this right here we call the line of reflection. We graph that with a dashed line. So that is my line of reflection. If I reflect I over that line, instead of going up 2, I'm going to go down 2. And that gives me I prime. Instead of going up 1, I go down 1. That gives me A prime. Instead of going up 5, I go down 5. And that is J prime. And so we see here, this is what the triangle would look like if it's reflected in the x-axis. And if I folded that, it would land right on top of itself here. Alright, so my new coordinates, J prime is going to be -5, -5. A prime is going to be -5, -1. I prime would be -1, -2, if we look at that. So now looking at 3, it says determine whether or not a reflection is an isometry. Well, you can take this guy here, and we can see with tracing paper that these are the exact same shapes, and so we would say it's an isometry because the angle, measure, and side length are preserved. Now if you don't have tracing paper, another way we talked about doing that is just showing that the length is preserved using the Pythagorean theorem. So I can do that by drawing in my right triangle. So if I did that here, we have 3 and 4, here, 3 and 4, and I can say that 3 squared plus 4 squared will equal Ji squared. And if I solve this equation, I get that 25 is equal to Ji squared. If I take the square root, I have this plus or minus 5 is equal to Ji, but I know that the length always has to be positive in a triangle, so we have Ji equals 5. And I can do the same thing for the image. 3 squared plus 4 squared equals J prime I prime squared. I can solve this, and I find that the side length is preserved. How we would say that in your explanation, this would be our work, but what I can say is that Ji is equal to J prime I prime. Therefore, side length is preserved. That's what that means. That's what that work shows. Now, in order to prove that this is an isometry, we need all of these, so you could do it for all of them. I'm only demonstrating for one, but you could do it for all of those different side lengths. The vertical segments, we can just count. We don't need the Pythagorean theorem because it's a vertical segment. And then the angle measure, at this point, all we can do is show that, that using tracing paper. All right. So the next part says examine the coordinates to determine a pattern of how the coordinates change from J to J prime, etc. Okay, so if we look at this, what I'm noticing is that the x coordinates remain the same, which makes sense because if I flip something over a horizontal line, that x coordinate, I'm not changing left to right, right? I changed from going up to down, but I didn't change left to right. So the x coordinates stayed the same, but your y coordinates each time became opposite of what they were. So instead of being up 2, I'm now down 2, which also makes sense. So I'm going to say these are opposite. And you can write that in words. For the coordinate rule, what we're going to write, I'd like you to try and come up with that on your own. So think through, how could you write that in a coordinate rule? So go down here, we'll start the notes for the summary. In the summary, we're going to say that a reflection is an isometry, and if we have a reflection in the x-axis, the coordinate rule will be you take your x and y coordinates, the x remains the same and the y becomes opposite, which means it is negative y. And that's how we write that notation. The next one we're going to do is a reflection in the y-axis. So if we take a look at that, here, a reflection in the y-axis, originally we had our figure like this. We reflected in the y-axis. Our image is now going to look like that. So we notice instead of being 1 to the left, we're now 1 to the right. Didn't change up or down at all. Instead of being 5 to the left, we're now 5 to the right, 5 to the left, 5 to the right. So I'm going to graph my line of reflection again. And here I can graph, I was 1 to the left, now I go 1 to the right, that's I prime. Here I was 1, 2, 3, 4, 5 to the left, I'm going to go 1, 2, 3, 4, 5 to the right, there's A prime. I was 1, 2, 3, 4, 5 to the left for J, 1, 2, 3, 4, 5 to the right is J prime. And it's always nice to have that tracing paper just to double check, right? So we have this guy here, traced it, flip it over the line of reflection. There we go, flip it over the line of reflection, and it lands exactly where it's supposed to. So now if I look at these coordinates, we are J, where are we? Positive 5, comma, positive 5. A is positive 5, positive 1, and I is positive 1, positive 2. So if we try to look at this coordinate rule, we're saying, well, this time the y coordinates stay the same, but the x coordinates are now opposite, which makes sense because we're not changing the y coordinate. We're not going up or down any. But if we used to go to the left one, now we're going to the right one. So if it used to be negative, now it's positive. And the opposite would be true as well. If we were on the right-hand side to reflect over the y-axis, I would then have to make it negative. So these are also opposite. Again, go back to your summary and try and fill in what the coordinate rule would be here. And then let's check our answer. Alright, so if you said xy would transform to the opposite of x and then keeping the y, you would be correct. So those are our coordinate rules. Now, I do not have these memorized. I just think through them every time. So I do not expect students to memorize this. I'd rather have you be able to actually do the transformation and understand transformations. But I think it's worth noting here as well that we do have coordinate rules, and it's another way to express these. There's one more transformation I want to talk about. You don't have to reflect in the x and y axis. You could also reflect in any line. And so we're going to start looking at different lines. The first line we're going to look at that is not the x or y axis. It's still a vertical line. It's x equals -2. So if I graph that, that's this guy right here. We have x equals -2. And this is an example of where we have points on either side. So if I look at I prime, I look to the line of reflection. It has to be the same distance, but on the other side. So if I'm 1 unit away, I have to go 1 unit away over here. So I was 1 unit to the right, now I go 1 unit to the left. Well, A, though, was 3 units to the left. I now have to go 3 units to the right for A prime. And J was 3 units to the left. I now have to go 3 units to the right for J prime. And so now I wasn't always moving everything to the right or everything to the left. You just have to go to the opposite, the other side of the line of reflection. And there we go. So here, our coordinate rule, we go right 1, up 5, so that'd be 1, 5. For A, it's negative, wait, where are we at? We're 1, 1 now. And for I, we are -1. Oh no, that was our original point. Our image is -3, 2. -3, 2. What we can see is that our y coordinate stays the same. Our x coordinate is not just changing sign. There's something else going on here. So there is a pattern. This is kind of a more complicated rule, a more complicated coordinate rule. So if you can think through what the coordinate rule would be, that would be awesome. This is not something I expect every student to be able to do. But there is a pattern. It's just not as obvious necessarily as the other reflections. So we can reflect in any vertical or horizontal line. And in fact, we can reflect in any line, but this video we're just reflecting in horizontal and vertical lines. And so it doesn't have to be the X and Y axis. It could be any vertical or horizontal line. All right, and to wrap up this video, I want to take a look at the problems below. Here it says, draw a line through each point and its image. So through each point and its image. So if I do that, where is my, through each point and its image. There we go. There we go. If I do it to these other ones, we'd have these guys. Through each point and its image. Each point and its image, and so on. And finally the third one, I did that here. And what it's going to ask us to do is just draw some conclusions about this line we just drew and the line of reflection. So we're thinking, well, what could we say about the lines we just drew and the line of reflection? So what conclusions can you draw about the line of reflection, so what I have in blue, and the line connecting any point in this image, what I just drew in red? Go ahead and draw your own conclusions here. And let's see what we can get. When I look at this, what I recognize is that if the line of reflection is horizontal, these guys are now vertical. And the opposite is true here. If the line of reflection is vertical, these are horizontal. And when I think back to vertical and horizontal lines, their relationship means that they are always perpendicular. So one conclusion we can draw about reflections is that the line of reflection is perpendicular to the line containing any point and its image. That is one conclusion we need to draw. The second conclusion comes from the next question. What can you say about the distance from the point to the line of reflection and the distance from the image of that same point to the line of reflection? Well, when I look up here, the distance from this point to the line of reflection is 2. This distance is also 2. This distance is 1. This distance is also 1. This distance is 5. This distance is also 5. And if we looked at the other graphs, the same would be true. So we notice that the distance from a point to the line of reflection is the same as the distance from its image to the line of reflection. So, scooching down here, the distance from a point to the line of reflection is equal to the distance from the image of that same point to the line of reflection. These are two facts about reflections that we are more easily able to see when we reflect in vertical and horizontal lines, but we are now going to use that to reflect in the lines that are not vertical or horizontal. So these are going to be two very important facts that we can use moving forward.